Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the formation of base metal deposits. So the base metals is a group of metals that includes such well-known ones as iron, nickel, copper, lead, zinc. Now these metals are considerably more abundant than the precious metals, gold and platinum. The abundance of the base metals in the Earth's crust is considerably higher than the precious metals, and so this means that base metal deposits are often going to be a lot larger, and they're going to have a higher grade when you compare them to precious metal deposits. So in the case of base metal deposits, you're going to have a deposit which will contain ore which will often have percentages of the metal of interest. So you might have a copper deposit and the ore might be 1% copper. Compare that to something like a gold deposit where the amount of gold might be somewhere in the regions of a fraction of a percent. And so you can see that because there's more of these metals in the Earth's crust, the deposits that you're going to form are typically going to be larger and they're going to have more of the metal of interest within them. So we're going to begin by looking at iron deposits, and we're going to start by looking at banded iron formations, which are sometimes referred to as BIFs. So banded iron formations are a layered sedimentary deposit. So down here in the bottom left, you can actually see a photograph of a piece of banded iron formation. You can see that it consists of these layers of this rusty red material, which also has this kind of more browny orange color here. And this consists of chert, silica. And in between these layers of silica, we have these dark gray layers. These are iron oxide. So the first question is, well, what's going on to form them? Well, we need to begin by looking at when banded iron formation formed. So most banded iron formations formed between 2.4 and 2.35 billion years ago. So why is this? Well, it just so happens that this is the period of time in Earth history when the Earth's oceans began to essentially gain oxygen. Free oxygen began to be produced, and it was slowly dissolving into the ocean. We also notice that the formation of banded iron formations stops after 1.85 billion years ago. So this shows us that by that point, the Earth's oceans were fully oxidized. So there was dissolved oxygen in seawater. So, so we know that banded iron formations happen to coincide with the oxygenation of the Earth's ocean. And so the next question is, well, where is that oxygen coming from? And it's going to come from a group of microscopic photosynthesizing bacteria called the cyanobacteria. And they occur in a range of different environments. Some of them float freely on the surface of the sea, and some of them will form structures like these. These are called stromatolites. So each one of these lumps is an individual stromatolite, and it's made of layer upon layer of these cyanobacteria built up one on top of another until you end up with this dome-like structure. And so the thing about cyanobacteria is they photosynthesize, so they produce oxygen as a byproduct. So now we know where the oxygen is coming from that seems to be related to the oxygenation of the Earth's oceans, which happens to match the timing of the formation of banded iron formations. So the next question, therefore, is where is the iron coming from for these banded iron formations? And in this case, the iron is coming from two sources. So it's coming from the weathering of rocks from the continents. So the iron is essentially going into sediments or being dissolved in river water, and it's being transported out into the oceans via rivers. The other source for iron is from hydrothermal vents on the seafloor, pumping out hydrothermal fluids into the oceans, which contain significant amounts of iron dissolved within them. So the thing is that before 2.4 billion years ago, the world's oceans were oxygen free. And so because there was no oxygen in the oceans, when the iron went into the seawater, it didn't oxidize. And in modern conditions, if you have iron in seawater, the presence of oxygen in that seawater will react with the iron and it will produce an iron oxide, which is insoluble. So the iron will exit solution, form a mineral, and settle out. So before 2.4 million years ago, the world's oceans were oxygen free. So this meant the iron was going in, but it was never being oxidized. So it was just sitting in the oceans, in the seawater. And then all of a sudden, about 2.4 billion years ago, we see a sudden increase in the amount of oxygen being produced. And this is probably because the cyanobacteria are beginning to really take off in a big way. And so they begin to produce huge amounts of oxygen. Some of this oxygen begins to dissolve into the oceans. And when it does begin to dissolve into the oceans, all of a sudden the seawater begins to become oxygenated. And all of a sudden you have oxygen, you have the iron dissolved in the seawater, the iron and the oxygen react with each other, and they end up producing iron oxide minerals. And these iron oxide minerals then precipitate out of the seawater and settle onto the seafloor, where they start forming layers. So the next question is well, where is this happening? Banded iron formations appear to predominantly form on the continental shelf in relatively shallow seawater. And so why is this? Well, it's a simple answer. The cyanobacteria typically like shallower water than deeper water. And so where are you going to have the highest concentration of the cyanobacteria? Near the coasts in the shallower water. And because you have a higher concentration of the cyanobacteria, those areas will also have more oxygen in the seawater. And so the iron from the seawater will be removed more efficiently in those areas. So we now know where the iron came from, we now know where the oxygen is coming from, and we now can explain why banded iron formations appear to have this relatively limited time frame. So in terms of the banded iron formations themselves, as mentioned, they consist of these bands of iron oxide minerals, which are the grey things, and these bands of chert, which are these red and tan coloured layers. Now, the reason for these repeating layers is uncertain. We don't know. They could be seasonal, for instance. So the layer of chert could possibly be formed during colder portions of the year, like the fall and the winter. So ocean temperatures decrease, the cyanobacteria become less active, so they produce less oxygen. And so this means in the continental shelf environment, you are having sediments being deposited which are dominated by silicate minerals. And so you end up with a layer of chert forming eventually once everything is metamorphosed. And then as temperatures start to get higher during the spring and the summer, all of a sudden these cyanobacteria begin to become more active, they begin to produce more oxygen, and this means that you suddenly get an increase in the amount of iron oxide minerals being precipitated, and so you end up with a layer of iron oxide minerals. And then of course you go back to fall and winter conditions, you get another layer of chert, then the next year you get the summer and spring conditions, you get another layer of iron oxide, and so on. And so there is a possibility that each one of these pairs, these chert iron oxide pairs, represents 1 year. But we don't know for certain. Now, in terms of banded iron formation grades, they will typically contain between 20 and 68% iron. And these things are huge. So this is because you are essentially forming them from iron dissolved in the oceans. And the oceans are very, very large, which means that there was a lot of iron to be precipitated out onto the seafloor. And so banded iron formations will often have tonnages which range from the tens of millions of tons of ore to billions of tons of ore. So these are absolutely massive deposits. And they are the primary source of iron which is used by humans. Okay, so now we're going to look at one of the other types of iron deposit. These are replacement deposits which are located near intrusion. They're a type of deposit called a skarn. So as any intrusion crystallizes, incompatible elements will be left behind in the remaining magma. So we've mentioned previously that as a magma crystallizes, it will use compatible elements to form common minerals: feldspar, micas, pyroxene, olivine, quartz, etc. So the elements that are used to make those are considered to be compatible elements. However, there's going to be a whole range of elements which are not being used. These are the incompatible elements. And so these will be, elements like, for instance, uranium, lithium, manganese, for instance. They're not really being used to make silicate minerals, so they just get left behind in the magma. And of course, as the magma crystallizes, the amount of liquid left gets smaller and smaller and smaller. And so concentrations of these incompatible elements get higher and higher and higher because the volume of magma is constantly decreasing. So what happens is you end up with this residual magma right at the end of the crystallization process of your intrusion. Now, the thing about this magma is it will be full of these incompatible elements, and it will also be water rich because under most circumstances, water is a relatively incompatible element in igneous systems. And so right at the end, this water rich magma will boil during the very late stages of crystallization. And as it boils, it pushes into the surrounding rock. And if that surrounding rock happens to contain limestones, the hydrothermal fluid from the intrusion will react with those limestones. And by far and away, the most common base metal in these late stage magmatic hydrothermal fluids is going to be iron. And so what we end up with are these iron-rich skarns that form along the edge of these intrusions, where this magmatic hydrothermal fluid reacts with these layers of carbonate rocks. So these skarn deposits are associated with intrusions that have compositions ranging from mafic to felsic. So they form over quite a broad range of magma. And we also find them in intrusions associated with island arcs and continental arcs. So they appear to be mostly focused where we have convergent plate boundaries, or where we had convergent plate boundaries at some point in Earth history. So the reaction between the fluid from the intrusion and the carbonates produces a range of calcium, magnesium, and iron silicate minerals. So you're going to see garnet and pyroxene quite commonly in skarns. You're also going to see carbonate minerals forming. You're going to see oxide minerals forming, such as magnetite and hematite. Those are iron oxides, or scheelite, which is tungsten oxide. And you're also going to see some sulfides forming, such as copper sulfide. And so if you look here, you actually have two examples of skarns. So in the case of the one on the left, you can see that a lot of it is this dark grey metallic mineral. This is an iron oxide mineral. This is magnetite. And within it, you have these kind of brown colored crystals. That's garnet. Over here on the right, you can see we have another skarn. This one consists of a mixture of pyroxene, calcite, and garnet. So the garnet is the brown mineral, the pyroxene is the green mineral, and the calcite is the blue mineral. And this is a relatively common assemblage associated with skarn deposits. Now, skarn deposits are quite common. However, they are typically quite small. They do have very high grades, but there's normally not enough ore to really make them as economically viable as banded iron formation. Banded iron formations are the gold standard when it comes to iron deposits. These skarns, they're good. You do occasionally get one that's big enough to be successfully mined, but the majority of them are just too small. Okay, so now we're going to move on to copper deposits, and we're going to start with a group of deposits called porphyry coppers. So porphyry copper deposits are associated with intermediate magmas, intermediate intrusions, which were emplaced along convergent plate boundaries. So porphyry coppers form where you have orogenies going on producing mountain ranges. So these convergent plate boundaries, so ocean-ocean and ocean-continent plate boundaries. So the term porphyry refers to the presence of porphyritic texture. And porphyritic texture means that when you look at the rock, you see a mixture of large crystals sitting within a ground mass, a matrix of smaller crystals. And so when we look at our porphyries, the igneous rocks that contain mineralization, we will see that same texture. So if we look down here, we actually have a picture of some rock from a porphyry copper deposit. And if we look at one of these classes, let's look at this one right here, you can quite clearly see we have these very obvious lighter flecks in the rock. These are going to be these larger crystals, and around them you have this darker matrix, this darker ground mass, that's going to be made of finer crystals. So this rock that contains these two obvious different sized crystal sets, that's going to be your porphyritic texture. And so we would classify that rock as porphyry. So how do we form porphyry copper deposits? Well, we begin by having a magma that's moving into the crust. And as that magma moves into the crust, it becomes stuck. It gets stuck and forms a magma chamber. And the composition of this magma is going to be intermediate, and it's formed at a convergent plate boundary. So as the magma crystallizes, once again, our incompatible elements are going to become concentrated in the residual magma. So this is going to be elements including copper, molybdenum, and gold. And so just like the skarn deposits we were talking about, during the final stages of the intrusion crystallizing, we're going to end up with a water-rich fluid forming, which is going to contain our incompatible elements. And this fluid is going to push into the surrounding rock, fracturing it. And so it's going to create breccias around the margins of our intrusion. And so if we look at the diagram here, here is our intrusion. Here is the water from the magma pushing out, and it's going to create a shell of mineralization around our intrusion. Now, the intrusion itself is also going to lead to the circulation of groundwater, and so that will then take some of this mineralization, it will redistribute it somewhere else. But the mineralization from porphyry coppers is typically associated with the margins, with the sides of the parent intrusion. They'll typically form like a halo around. So if we look at the mineralization that we find in these porphyry coppers, what do we see? Well, as I mentioned, this hydrothermal fluid pushes into the surrounding rock, fracturing it. And so this is a piece of porphyry copper from the Bingham Canyon mine in Utah. And you can see over here on this side, you can see this region has clearly been brecciated. It's been broken up by the hydrothermal fluid pushing through. You can see here's some quartz from the hydrothermal fluid, and here we have pieces of the host rock which have been broken off to form the breccia. You will also notice that this sample has several bands in it which look a slightly darker brown compared to the rest of the sample. You can see it here. This has got a slightly rusty color to it. Same thing here, same thing here. So what are these? Well, these are the veins that contain sulfides, which have been formed from that hydrothermal fluid. So as mentioned, the mineralization, it occurs along the margins of our intrusion, and it's often referred to as a shell because it forms a shell-like structure around the edge of the intrusion. In terms of the type of mineralization that you get your mineralization hosted within the veins, or you get it disseminated throughout the rock. So a dissemination is just like, imagine a fine cloud of copper minerals distributed evenly throughout your rock. That's a disseminated mineralizing style. So you get very small crystals disseminated throughout your rock. So there's no really focused points like a vein. Instead, the mineralization is just everywhere within your volume of rock. So in terms of the mineralization itself, it's dominated by pyrite, which is iron sulfide. Now, pyrite is not an economic mineral, so actually not that important, but it does make up the majority of the sulfide mineralization. The main thing that we're looking for, though, is this. This is chalcopyrite, this is copper iron sulfide, and this is the mineral that we're most interested in because this can be used to produce copper. Some regions of the shell will also contain molybdenum in higher concentrations. And so the molybdenum will be present as the mineral molybdenite, which is molybdenum sulfide. And you will also have low gold grades throughout the entire shell. So if we go back to the previous diagram, what we tend to see is the inner portion of the shell closest to the intrusion tends to be more molybdenum rich. And then as you move away from the intrusion, the shell tends to become more copper rich. But within the molybdenum rich regions and the copper rich regions, you do get some gold mineralization as well, mixed in with the sulfide minerals. Now, porphyry copper deposits typically have pretty low grade, so they're normally less than 1% copper, and most of them contain equal to or less than 0.5% copper. So these aren't, particularly rich in terms of the grade of the ore. However, they make up for it by scale. And so when you look at the tonnages of porphyry coppers, they are huge. And the tonnages of porphyry copper vary between 100 million tons, with the largest porphyry copper coming in at 26 billion tons of ore. Absolutely massive. And that's because they are related to intrusions. And some intrusions are absolutely huge. And so when that intrusion crystallizes, it's going to form a large porphyry copper deposit, providing it's the right type of intrusion forming in the right kind of place. Okay, so next we're going to move on to another type of copper deposit. These are the volcanogenic massive sulfide deposits, which is often abbreviated to VMS deposits. So VMS deposits form along divergent plate boundaries where seawater gets pulled down into the crust and is heated by shallow intrusion dikes. So this is our divergent plate boundary. So we have extensional tectonics going on. So we have this block is moving over to the left, this block is moving over to the right, and the crust in the middle is being stretched and it starts to break and it fails, producing normal faults. So we get this distinctive step-shaped feature. This is our rift valley. So these normal faults are absolutely perfect because they allow seawater to move down them. And as that seawater moves down the faults, it becomes heated by shallow intrusions and dikes in the oceanic crust. The seawater then gets heated up. And of course, as it gets heated up, it becomes more buoyant. And so it wants to rise and it begins to rise back towards the seafloor. So the hydrothermal fluids that form from the seawater being pulled down and heated will typically have a temperature somewhere around 400 Celsius. So, this is very, very hot water. And as this very, very hot water passes through this upper portion of the oceanic crust, it scavenges metals as it goes. And it will scavenge iron, copper, lead, zinc, silver, gold, sulfur, and a range of other lesser elements. And so what's going to happen is, as mentioned, this hydrothermal fluid is circulating around. It's scavenging metals as it goes. It's also getting heated, so it's becoming more buoyant. It's going to rise to the surface. And eventually, this hydrothermal fluid is going to vent onto the seafloor. And so when this hydrothermal fluid vents onto the seafloor, it's going to have a temperature of around 350 Celsius. And it's going to come in contact with seawater that has a temperature of approximately 2 Celsius. So between the two fluids, you have a difference of about 348 Celsius. So this is a very significant temperature change. And so because of this, the hydrothermal fluid very rapidly cools and you have fluid mixing taking place. And so because of this, it encourages the sulfides to exit the hydrothermal fluid and precipitate onto the seafloor. So what does that actually look like? Well, here is a nice example of a hydrothermal vent on the seafloor. This is from the Mid-Atlantic Ridge, so in the middle of the Atlantic Ocean. And so this cloud of dark, essentially smoky looking material is the hydrothermal fluid coming out of the seafloor. And so this is going to have a temperature of about 350 Celsius, but it's in contact with water that has a temperature of 2 Celsius. So this very rapid cooling encourages the precipitation of sulfide minerals from this hydrothermal fluid. And so what you end up doing is you end up building these chimney structures, which are made of sulfides. They're going to be mostly iron sulfides, so pyrite, but within them there's also going to be copper sulfides, lead sulfides, and zinc sulfides. And you can also see another example here. So these are extinct vents. They're no longer active anymore, but you can see this chimney-like shape to them, which was formed by the hydrothermal fluid. And all of these extinct vents are essentially made of sulfide. So the vents themselves are often referred to as black smokers because the hydrothermal fluid venting out of them will often produce this black cloud-like appearance. So as mentioned, the sulfides that make up these chimneys are primarily formed from pyrite with lesser copper sulfides, lead sulfides, and zinc sulfides. And over time, you get a buildup of sulfides on the seafloor around the vent. And so this is because the vents themselves, these chimneys, are constantly breaking. So bits of them are constantly falling off and settling onto the seafloor. And you have to remember, this is going to go on over a period of hundreds of thousands to millions of years that these vents will be active. And so over time, you end up building up a huge layer of sulfide minerals on the seafloor due to the venting hydrothermal fluids. You will also get a substantial buildup of sulfide minerals just underneath the chimneys in the subsurface. So here are our sulfide vents. These are our black smokers on the seafloor. And you're going to build up sulfides on the seafloor due to the chimneys, but you're also going to build up sulfides underneath the volcanogenic massive sulfide deposit as well, so underneath the vent. So you're going to have sulfides forming on the seafloor and under the seafloor as well. And the area underneath the vents essentially is the plumbing that's feeding the vent. So that's the area that the water, the hydrothermal fluid, is passing through to vent onto the seafloor. But as it's moving up, it's cooling down, and so it will begin to precipitate some minerals as it cools. So the sulfides can then become buried by sediments, or they can be covered by flows of basalt, and this will help to preserve the mineralization. So in the case of these extinct black smokers here, these extinct chimneys, what you can see is we actually have some volcanic eruptions which have deposited basalt, and we have this fine layer of sediment over everything as well. And so over time, as long as nothing drastic happens, these chimneys, these sulfide chimneys, will eventually become buried, and by becoming buried, they will then be preserved. So the next question and final question that you've probably thought of is, hold on a minute, this is all happening in the oceans. And obviously, this happened millions of years ago. It's been going on for a very long time to form these deposits in the past, and that's what we're mining now. But if they formed in the oceans, how did they get onto the land? So obviously what's going to happen is you're going to have a situation where the oceanic crust that contains this type of mineralization is obviously going to have to be pushed onto the continental crust so that we can access it. And that's primarily going to happen in the form of things called ophiolites. So an ophiolite is a piece of oceanic crust that's simply been pushed onto the continental crust through a process called obduction. So subduction is when the oceanic crust goes under. Obduction is when the oceanic crust gets pushed on top of the continental. And obviously, as that piece of oceanic crust gets pushed onto the continental crust, it's going to bring any mineralization in the oceanic crust along with it. And so this is going to allow these mineral-bearing pieces of oceanic crust to become accessible to us because they have been pushed onto the continental crust. I should also point out that there are some companies that want to undertake seafloor mining to actually directly mine the black smokers, and it's looking like there may be some attempts to actually do this in the next few years. However, there are very serious environmental concerns about it. So at the moment, it's still not exactly certain about whether this seafloor mining will be allowed to. We'll have to find out in the future. So the final type of copper deposit we're going to look at are sediment-hosted copper deposits. And the origin of sediment-hosted copper deposits is hotly debated in geology. We don't have a definitive explanation to explain them. So the mineralization in these sedimentary hosted copper deposits, the mineralization is hosted in limestones or dolostone, so carbonates. You can find it in sandstones, conglomerates, and mudstones. So there's a whole range of different rock types that can host this type of copper mineralization. And it appears that the mineralization is located in areas where fluids are mixing or where you have a reducing rock. So it looks like either you have two different fluids combining at a location, one of them contains the copper, and the mixing of the two fluids causes the copper to come out of solution and precipitate to form minerals. The other option is that you have a chemical reaction between your copper-bearing fluid and your rock, and that chemical reaction between the two once again results in copper minerals being formed. Now, when we look at the mineralization, we'll find that it might be hosted in pores between sand grains. We might find it replacing earlier minerals like carbonates. We might find it replacing fossils. We might find the mineralization replacing earlier sulfide minerals. Or we might find mineralization within voids in our limestone, in our carbonates. So there's a lot of variation in these sedimentary copper deposits, and that's what makes them so difficult to explain, because there's a lot of stuff going on, and each deposit is different to the next one, and so it's very difficult to come up with a definitive model that explains all of them. So in terms of the fluid that's carrying the copper, it appears to move along faults. It will also exploit boundaries between rock layers, and it will move along porous layers of rock, so it will move along aquifers. And the source of the copper is also uncertain. It could be copper that's being scavenged from rocks as the hydrothermal fluid passes through it. It could also be fluids which are being produced by liquefaction of sedimentary rocks. It could be hydrothermal fluids which are being formed by from magmas. It could be even be hydrothermal fluids being formed by metamorphism. We really aren't sure. But all we know is that there is some kind of copper-bearing fluid moving into these sedimentary layers, and this copper-bearing fluid is reacting with these layers of rock, and it's resulting in the precipitation of copper minerals. So I'm sorry I can't give you more information really about sedimentary copper deposits, but it's quite a complex topic, and there's a lot of fine nuanced detail that we don't need to cover. Okay, so the next thing we're going to concern ourselves with is, well, how do these copper deposits weather? And this is very, very important, especially for porphyry copper deposits. So porphyry copper deposits are typically quite low grade. So they're going to be less than 1% copper, with the majority of them being less than 0.5% copper. However, the grade can be increased by leaching copper mineral. So how do we do this? Well, the first thing we need to do is we need erosion to help us. So erosion needs to remove the rock overlying our porphyry copper system. And as that rock is eroded away, our porphyry copper system becomes exposed to the atmosphere. And because our porphyry copper is exposed to the atmosphere, it's going to react with rainwater, so meteoric water, and oxygen in the atmosphere. And this is going to cause the pyrite to break down. Pyrite within our mineralization is going to react. And so what does this do? Well, when you take water, oxygen, and pyrite and mix them together, what you end up forming is sulfuric acid. And you will also form iron oxides as a byproduct. And the most common iron oxide is a mineral called limonite or limonite, and it has this very distinctive kind of slightly brown, red-brown, rusty color to it. And so you can actually look at this picture here, and you can see the area here which has limonite buildup in it because it has this kind of brown, rusty brown color to it. So, okay, so we have our water that's interacting with our porphyry copper. And as it reacts with our porphyry copper, the water is becoming more acidic because pyrite is breaking down and it's forming sulfuric acid. And so our rainwater is now very, very, very weakly acidic. And so as it moves through the porphyry copper system, it begins to dissolve the copper mineralization. And so this water moving through our copper deposit begins to dissolve the copper mineralization, and that copper is now entering solution. And so what's happening is in our leached area where the copper is being removed from, we are essentially destroying sulfide minerals, and in their place, we are producing this limonite, this iron oxide mineral, and that's going to give the leached area this distinctive rusty red color. Now, what's going to happen then is this copper-bearing water is going to move down through the intrusion, through the porphyry copper deposit, under gravity. So the copper-bearing water is going to keep dropping, and eventually it's going to meet the water table. So if the water that makes up the water table, so this is groundwater, is oxidizing, so there's oxygen present, the copper minerals are going to precipitate out, and they're going to form copper oxides and copper carbonate. So we're going to see minerals like cuprite, which is copper oxide, or malachite and azurite, which are copper carbonates forming. Now, if this water here is anoxic, so water poor, we're going to form copper sulfide minerals. And so we're going to form minerals like covellite, chalcocite, and digenite. And so, well, what does this actually mean? Well, if we look at this picture here, we can see a porphyry copper system, and right up at the top here, you can see this rusty red area. This is a portion of the leached cap. And then beneath it, you will notice that the porphyry copper has this very distinctive kind of greeny blue color to it. And so this is the reprecipitated copper mineralization. And in this case, for this particular mine, the copper mineralization consists of azurite, which has a very strong blue color, and malachite, which has a very strong green color. So that means the groundwater here was oxidizing. And so this green and blue color combines to give us this very obvious green-blue color to the rock. And this is actually a piece of the ore from this region. And you can see the dark blue azurite here, and you can see the strong green malachite as well. And both of these are copper minerals. And so what happens is by remobilizing this copper mineralization, reprecipitating it somewhere else, you are actually increasing the grade. So what you're doing is you're taking all the copper from this region and you're precipitating it back out in this thin band right here. So this portion of our porphyry copper is going to have considerably higher copper grades compared to other parts of the porphyry copper. So these new copper minerals that are building up are referred to as supergene mineralization. So it's secondary mineralization, it's not primary. And this buildup of supergene copper minerals along the ancient water table will produce a region in the deposit that has elevated copper grade. And when you mine your porphyry copper, you will typically try and mine these regions first, because this is the highest grade copper ore. And so when you process it and sell the resulting concentrate, you're going to make more money. And so, if you want to pay for the cost of building the mine, and so that means you're going to mine this area first because it's going to earn you the kind of money that will allow you to begin paying back the cost of mine construction. Okay, so let's look at another type of base metal deposit. We're now going to look at lead zinc deposit. So lead and zinc tend to commonly occur together in deposit. So there are several different types of lead zinc deposits. They can also sometimes have copper mineralization as well, and sometimes there can also be some silver mineralization there along with the lead zinc. So these deposits can be primary, so they can be formed when the sediment was deposited. And remember, the mineralization is going to be hosted in sedimentary rocks. So your lead zinc deposits can either be formed at the same time as the sediments, or they can be secondary. They can form after the sediments have turned into rocks. So primary deposits include lead zinc volcanogenic massive sulfide deposits, a group of deposits called the Irish type deposits, and a group of deposits called SEDEX deposits, and that stands for sedimentary exhalative deposits. And these are all types of lead zinc deposits that form when the sediment that hosts them is also being deposited at the same time. So they are primary. Secondary lead zinc deposits includes the Mississippi Valley type deposits, and these are formed due to the replacement of carbonate rocks by minerals from hydrothermal fluids. So in all of these instances, the metals, the lead and zinc, are being transported in hydrothermal fluids which formed during the burial and liquefaction of sedimentary rocks or due to the heating of magma. And so these fluids are circulating through our sequence of sedimentary rocks, and as they circulate through our sequence of sedimentary rocks, they are picking up, they are scavenging lead, zinc, copper, silver as they go. So in terms of the primary deposits, they are going to form where our hydrothermal fluid vents onto the seafloor, so just like a VMS deposit. And this change in temperature is going to cause the sulfides to precipitate out. In the case of secondary deposit, it's all about a fluid reaction. So we're going to have our hydrothermal fluid reacting with reactive rock. So we're looking at carbonates, or we're looking at mudstones that contain large amounts of carbon. And this once again is going to encourage the lead and zinc to leave the hydrothermal fluid and precipitate out as solid minerals. So the final type of deposit we're going to look at are the Sudbury nickel deposit. And to be very clear, Sudbury nickel deposits are an anomaly in Earth history. Okay, Sudbury is the only place that this type of deposit formed, and the process that formed it is extremely unique. So the Sudbury Igneous Complex is a body of igneous rock that formed about 1.85 billion years ago, and it was produced by a meteorite impact. And that meteorite impact occurred just off the coast of a supercontinent called Nuna. So the impactor that caused the meteorite impact was about 10 to 15 kilometers in diameter, and it initially produced a crater that was 30 kilometers wide and about equally deep. And unfortunately, the sides of this crater were naturally unstable, and so the sides of the crater went and failed. And so this meant that because the sides of the crater started to fall into the crater, we ended up taking our 30-kilometer wide crater, and it became a crater that was between 150 and 280 kilometers in diameter. So very, very large. So the Sudbury impact is considered to be one of the big three impacts that have occurred in Earth history. So the impact itself obviously produced a crater, and within that crater there was a sheet of intermediate composition magma, which was produced by the melting of the rocks that got hit by the meteorite. So from this intermediate magma sheet, we see that sulfide and precious metal minerals began to crystallize. And these metals were denser than the surrounding magma, and so they began to sink to the bottom of the intrusion. So we've already heard this story before when we were talking about platinum deposits in the Bushveld. And so these dense minerals settle through the magma and they form a layer on the seafloor. And you can see these layers in the diagram right here as this dark grey material. So some of these sulfides just ended up sitting on the bottom of the intrusion, and some of them actually went down large cracks in the footwall underneath the intrusion, and so they ended up forming these deposits that pushed into the rock which underlied the intrusion as well. So the question is, well, okay, it's a relatively straightforward mechanism to form the mineralization, but how do we actually know it's an impact crater? Well, we know that the Sudbury Igneous Complex is an impact crater because we can see indicators. So if you look at this picture here, you can see you have these distinct striations on the rock face. These are shatter cones, and they are produced by the pressure waves given out when the impact occurred. So this is a very common thing associated with impact craters. We also see the development of something which is referred to as pseudotachelite, and it's a type of breccia that's formed by the sides of the crater collapsing. We also see something referred to as fallback breccia, and this is a type of rock which is produced when all the material that got blasted into the atmosphere by the impact falls back into the crater, and it creates a layer of rock which is referred to as fallback breccia. And the final thing is there is an iridium anomaly. And so iridium is an element that is commonly associated with meteorites. It's not very common on Earth. So when we do find iridium in higher concentrations, one of the possible reasons for that is, well, a meteorite came flying in from space, hit the Earth, and that area became contaminated by the meteorite, adding iridium to that area. And so when we look at the Sudbury Igneous Complex, we have indications of an iridium anomaly as well. So all of this evidence combined tells us, yes, this was definitely an impact crater. So although attempts have been made to find similar styles of deposits at other impact craters, at the moment we have no other impact-related deposits anywhere on Earth that we know of. And so Sudbury is a completely unique type of mineral deposit. Okay, thank you for watching this very long video. I appreciate it. Good day.